Welcome to the Autolite Challenge Professional Technician Program. This module focuses on spark plug metallurgy and testing. The American Heritage Dictionary defines metallurgy as the technique or science of working or heating metals so as to give them certain desired shapes or properties, like the center electrode of a spark plug. When the first spark plugs were invented more than 100 years ago, the center electrode was made from a solid material. This application of metallurgy worked fine for more than 50 years. As time went on, the automobile was forced into a state of continuous improvement to meet competitive challenges and emissions regulations. So engineers and scientists developed high-performance, long-life spark plug electrodes and components. This created a much longer-lasting and more reliable ignition system with improved combustion over a very long service interval. In the 1960s and 70s, it wasn't uncommon to have to service spark plugs every 10 to 15,000 miles. Now, thanks to improved ignition components, advances in metallurgy and materials, and cleaner oils and fuels combined with electronic engine controls, some applications can last as long as 120,000 miles before requiring replacement. In this module of the Autolite Challenge Professional Technician Program, we will discuss the characteristics of different metallurgic properties and how they apply to today's applications. We'll also show you how and why we rate and test spark plugs here at Autolite. Pure copper melts at close to 2,000 degrees Fahrenheit and has tremendous electrical and thermal conductivity, but it's very soft, so by itself, copper would make for a poor spark plug electrode. That's why when we describe our copper plugs, we refer to them as copper core, because only the core of the electrode is made of copper. The outside of the electrode is a nickel alloy. By using a copper core center versus a standard material, we can conduct more heat out of the combustion chamber and into the cylinder head and coolant passages. This helps minimize electrode oxidation and assists in lowering combustion chamber temperatures to minimize pre-ignition risk and help reduce NOx output, a harmful greenhouse gas. In the 1980s, this was quite a breakthrough in spark plug technology. Even today, you will still see a copper core center in a few applications, but the original equipment manufacturers will usually specify a 25 to 30,000 mile change interval for conventional copper core plugs. You should never use a copper core plug in a DIS application. The side wire is not designed to reverse fire like an Autolite double platinum or iridium enhanced XP spark plug. Using a copper core or single platinum plug will cause premature electrode wear on half a vehicle's spark plugs in as little as 18,000 miles. Platinum is an extremely rare metal that occurs in only about 0.003 parts per billion in our Earth's crust. Platinum is more precious than gold or silver and is much more resistant to oxidation than most other metals. It has a melting point of over 3,200 degrees Fahrenheit and a high resistance to chemicals that occur in the combustion chamber. Plus, it's a good conductor of electricity. As you can imagine, a precious metal like platinum can be very expensive. So why do we use platinum in a spark plug? As ignition systems evolved into electronic systems with fewer moving parts, a longer life spark plug was needed to match the durability and performance of these new ignitions. Platinum plugs provide a center wire platinum firing tip for reduced gap erosion, fewer misfires, better performance, and more durability. A platinum tipped center electrode resists oxidation and arc erosion and will maintain a constant gap over a much longer period of time versus a copper core spark plug. A platinum electrode spark plug tip can be as small as 0.8 millimeter and is considered a platinum fine wire design. So why do we need a double platinum spark plug? As the ignition system with a distributor evolved into a distributorless system, it fired the spark plugs in both directions. This means that half the spark plugs on a vehicle fire from the center electrode to the side electrode, and the other half of the spark plugs fire from the side electrode to the center electrode. A double platinum design helps to protect against side wire erosion from the plugs that fire from the side wire to the center wire electrode. If a vehicle has a coil pack DIS ignition, chances are it uses a double platinum spark plug. Iridium is a very hard, brittle metal in the platinum family that has a melting point of over 4,400 degrees Fahrenheit. Iridium is the most corrosion-resistant metal known to man, even under temperatures as high as 3,600 degrees Fahrenheit. It's also a very rare element. By comparison, platinum is about 10 times more common in occurrence. As ignition systems further evolved into coil-over-plug systems and coil-near-plug systems, it was important to develop a more efficient spark plug that required less voltage to fire. You can imagine that installing individual coils for every cylinder is a difficult and expensive task. The coils need to be made smaller with manufacturing costs under consideration and are often placed in tight underhood locations. The specific output of the smaller coils is lower, and plug manufacturers needed to find a way to lower the voltage requirement from the coil for the spark to jump the gap. Engineers discovered the best way to reduce firing voltage was to reduce the diameter of the center electrode. As the diameter of the electrode grew smaller, manufacturers needed a superior alloy to handle an increased amount of arc erosion over the smaller electrode diameters. Today's iridium alloy spark plug electrode can be as small as 0.4 millimeters. By itself, iridium is not as resistant to oxidation erosion as a platinum electrode until it's blended with other metals like platinum and tungsten. Some manufacturers now specify iridium fine wire technology in coil pack DIS applications because of its superior performance and durability as compared to large wire platinum designs. In any event, iridium and fine wire plug designs are the technology behind the 120,000 mile spark plug change interval. Now let's talk a little more about oxidation. Oxidation forms as a result of the combustion process. Oxygen reacts with the electrode materials and causes them to degrade and erode faster. As the electrodes oxidize, they become scaly, and the weakened material peels away from the electrode faces, causing the electrodes to wear. Some metals oxidize at higher temperatures. That's why we select different metallurgy for different design criteria. It's important to select electrode materials that are naturally resistant to oxidation as well as electrical arc erosion. That's why we use expensive platinum and iridium blends to create effective alloys for the job. Now here's a rundown of some of the other metallurgy surrounding spark plugs. The word tungsten comes from the Nordic word that means heavy stone. Of all the materials in their pure form, tungsten has the highest melting point, nearly 6,200 degrees Fahrenheit. Tungsten oxidizes at lower temperatures than other metals and would be a poor performer all by itself. Blending iridium and platinum and tungsten creates an alloy that combines and exploits the benefits of each material. Nickel is a corrosion-resistant element that is often combined with copper to form a copper core spark plug electrode. It's also used in plated form to provide a corrosion-resistant spark plug shell that resists seizing in an engine spark plug threads. You can see that there's certainly a science behind spark plug metallurgy and some pretty expensive metals involved. Keep that in mind the next time you buy, sell, or install a set of spark plugs. Now that you know that precious metal plugs are specifically designed for modern ignition systems, you can choose the correct design for the right application. This is a spark plug rating engine. It's one of the key pieces of equipment that we use to test Autolite spark plugs against other OE plugs to figure out exactly what their heat range actually is. This engine is a one-cylinder variable boost engine that runs on benzene. We put a spark plug in it and run it through a test cycle. Every cycle we advance the boost of the supercharger, increasing engine output until the spark plug goes into pre-ignition and the torque output drops off. From this data, we generate a data point called IMEP, which stands for Indicated Mean Effective Pressure. IMEP is the measurement of the average work produced during one engine cycle. When we standardize all of the other test conditions, we can rely on IMEP to determine a spark plug's ability to conduct heat away from the combustion chamber and to calculate the heat range. We can compare that IMEP number to an OE spark plug on the same engine to properly match our heat range and part number to theirs. Because ratings and rating engines can vary, we must compare all plugs at the same time on the same engine under the exact same conditions. We do not rely on published data, as the test will most likely be administered under different parameters. We can also use this rating engine data to make sure that our production is meeting the correct heat range. This is the machine that we use to do just that. For obvious reasons, we call it a rating engine. One of the questions that we get asked all the time is, how can we sell or recommend an Autolite spark plug when it's not the original equipment spark plug for an engine? This is why a rating engine is extremely important. Now, this is an OE spark plug design, and this is an Autolite spark plug. Obviously, we start by comparing the dimensions to make sure the ceramic projection is the same, the thread length is the same, the hex is the same, the insulator is the same, and so on. But that's just the beginning. We need to find out the exact heat range of the OE spark plug design. This is very important because if the heat range is too cold, the spark plug could exhibit misfiring or cold fouling, or may not even start if it's too cold outside. If a plug is too hot, an engine may suffer engine-damaging pre-ignition when the engine's under a heavy load. What we'll do is take a sample, like 10 or 12 of a competitor's plugs, and run them through this rating engine to generate the IMEP number. Remember, IMEP is a numerical value we use to define heat range. We'll use that heat range information to correctly match our heat range to the OE application. That's why time after time an Autolite spark plug will start when it's cold and resist pre-ignition when you're towing a trailer up a hill. We also perform impact testing that simulates real-world situations, like accidentally dropping spark plugs on a shop floor before you install them. We work hard at designing insulators that combine strong mechanical strength with strong dielectric strength. That's a plug's resistant to insulator breakdown or failure. A pull test is performed on the terminal stud to ensure the plug will survive a situation such as a stuck spark plug wire. And we put our resistors through testing to ensure they will last 100,000+ miles. In our laboratory, we also use an SEM, or scanning electron microscope, to determine metallurgical properties of production samples and actual competitors' products to ensure that they are what they say they are. We also perform non-destructive X-ray testing to look inside a spark plug without destroying it. You may think that since spark plugs have been around for so long, all of the hard work and innovation is long over. But the truth is, generations of ignition engineers at Autolite have been hard at work to make some of the finest spark plugs in the world. Thank you for your time.